Okay. Last time we had to stop the class abruptly uh, since I had a doctor's appointment for my son. Uh, and we are today, I'm meeting you after huge disaster. Probably we got the heaviest rainfall after 60 or 70 years to Kandy. And the disaster was huge because, Kotmale gates are open amid the, amid of the heavy rainfall. Therefore, the disaster was also huge. Probably the loss is like trillion rupees, or more than 1 trillion, and loss of lives, loss of family members, and loss of assets and stuff like that. Uh, anyway, exam will be postponed by 1 week, I suppose. Assuming that it won't be postponed, we'll do our work. Hmm. I hope you guys are okay. Uh, Even though you have a loss, it will be a recoverable loss, right? Okay. We started um, exponential functions, right? We went through, trigonometric functions in section 4. Then in section 5, we went through inverse functions. Section 6, Right. Uh, Again, we'll start. So natural exponential function and the natural logarithmic function. We in fact went through the natural exponential function. I just briefed through this because we had to stop the class abruptly last time. Therefore, I just continue with this. So I don't give you time um for you to take this down, but I'll just go through what we did last time. Now, natural exponential function is there to model certain phenomena that may encountered in day-to-day life. Like if something is there, for example, say, like during a pandemic period, during a period of pandemic, if you have more patients at the beginning, uh, you will have more patients at the end, like that. Hmm. Or if you have, let's say, more young couples, you will have more babies after a certain time. It's like that. So they want to model it like this. Uh, the growth will be like something like this. Hmm. Say, for example, uh, at t, say this is 0, this value is say doubled. So at 2t, this value will be doubled, right? Say this is h, this should be 2h, something like that. That shape should be there. So when it is at 3t, it should be 4h. So then it's like a power function or something, the power of something. Therefore, uh, you can assume that it is just, I mean, if you want to normalize it, you can assume that it is 1 when t is 0, right? This is a time axis. Now, if you want to construct the function in terms of x, you can, and on the other hand, here, you construct this in this way. Old is the value of the function. As I told you, if you have more new couples, you have more babies, like that. If you have more infected people, you will get more patients towards the end. So value of the function is equal to rate of change of the function. So we need these, I mean, to come up with this function. At 0, it should be 1, and the value of the function should be equal to the rate of change of the function. If this is fx, let the function be fx, then it should be equal to the rate of change, or f dash x. F dash x is the rate of change. Okay? Rate of change, or if the original function is fx, this is f dash x, the rate of change. And on the other hand, because of this, right, we need this. Also, f naught should be 1. I mean, these type of, I mean, a function that can be differentiated several times can be, I mean, it's called an analytic function, but that is something beyond our scope. You can always come up with a power series. That means it's not exactly a polynomial. It has infinite powers of x, and on the other hand, it should contain a sum of non-negative powers of x. It should be like this. I'll do it here. Let fx be something like this. This is the term corresponding to x to the power 0, this x to the power 1, this for x to the power 2. We went through this last time, but if I just start the lesson from there, then if a person just goes through this for the first time, he or she may not be able to understand it. So that's why I'm starting from the scratch. But those who were there in the class don't have to take this down. Now this is fx. Now use this first. Now if naught is 1, I'll plug in 0 for x. If you plug in 0, you know this will be 0, 0, everything will be 0. You just get a naught. And since f naught is equal to 1, a naught is 1. So basically, at least, we can figure out what a naught is. Now, our objective is to figure out these constants. Now, fx is equal to f dash x. Now, I am going to find f dash x. I'll do it here. F dash x is the derivative. Now, if you differentiate this, it will be 0. I'll write one more term, but it's an infinite series. If you differentiate this, it will be 0. If you differentiate this, you get a1. This is, a2 times 2x. So I'll write 2a2x. This is a3 times 3x squared. This is a4 times 4x cube. Something is wrong, right? This should be x squared. Because when you differentiate this, the power will be down by 1. Now, fx is equal to f dash x. You use that. Now, fx is this. Sorry. Is equal to, I'll write this for f dash x. Now we'll compare the coefficients. Here also you have infinite terms. By comparing the coefficients of x to the power 0 means constants, you have a naught is equal to a1. However, a naught is 1. We already found it, right? A naught is 1. So from that, you get a1 is equal to 1. Now go for x to the power 1. Here the coefficient is a1. Here the coefficient is 2a2. a1 is 1. So this is half. Now coefficient of x squared. Here it is a2. It is 3a3. a2 is half. To go for one more. This is a3. This is 4a4. This is, this is 1/6. This is 4 times a4. Now divided by 4. You get this. Now you can find the series. Now e to the power x is, not e to the power x, f naught. Sorry about it. fx. Now fx is this. I write everything again. A naught plus a1x plus a2x squared plus a3x cube. Now we'll plug in these things. A naught turns out to be 1 here. A naught is 1. This is also 1. Therefore, I just write it like x. A2 is half. Half means x squared over 2. This is 1/6. This 1/24. You know, there's a pattern here. This is 1 times 2. This is 1 times 2 times 3. This is 1 times 2 times 3 times 4. I'll write this as 1. I can write this as 1 times 2. It is not 1.2, 1 times 2. Right. You have something like that. Now there's a function. I mean, this is called factorial. We denote it by the exclamation mark because it's kind of. I'll show you why it's the most suitable way to denote it. This x squared over, 1 times 2. The largest integer there is 2. Here 1 times 2 times 3. You write it as factorial 3. This is factorial 4. And if you follow the pattern, now this should be factorial 0. 1, 2, 3, 4. I'm just going to introduce the factorial function. Now with this setup, I'll come up with factorial function as well as the series together. I mean, both together. Now look at this. Factorial 1 is just 1. Factorial 2 is 1 times 2, which is 2. The actual value is 2. Factorial 3. Look at this. This 1 times 2 times 3, which is 6. Factorial 4. So far, the numbers are so small. Factorial 4 is this. Put a white color, right? 1 times 2 times 3 times 4, which is 24. So far, the numbers are so small. We'll see what happens if it is like factorial 10. It is 1 all the way to 10. It is something like that. More than 3 million, right? A factorial 69 has more than 100 digits. So it is like that. It's the fastest growing function in a way. Now this is a fix. Now I'll rewrite the series for that. And on the other hand, what I want to say, the most is this. Factorial 0 is 1. It has a different definition. Separately, factorial 0 is 1. It has a different definition. However, that follows from this shape. This should be 1 over 1. So 1 over factorial 0 should be 1. Therefore, this is 1. 1 over 1 is 1. So factorial 0 is 1. That's the definition of factorial function. Now, I am ready to give you uh, the series of the exponential function. Look, this has a like power function, I told you. Since it's a natural exponential function, I'll use e to denote that. Like it may be like, 2 to the power x or 3 to the power x or something like that. But it should be, in fact, I write fx now. Now, factorial function is so. And in fact, we need this in algebra, in particular in problem 4 of PO math paper, which is binomial expansion. And again, we need that in problem 12, part A or part B, which is permutations and combinations. And sometimes in probability you need that, but which is not discussed in A levels. There's a thing called binomial expansion. You need factorial there. So you better have a little hang of factorials. So this is the first time we encounter factorial function. Hmm. But we later, I mean, towards the end of the syllabus, we again go through this factorial function. Hmm. Now fx is something like this. I'll take this 4. But I have to replace these by factorials. I just write the very first two terms as 1 and x. Then I write this as factorial 2, factorial 3, and x to the power 4 over factorial 4, like this. Now, since this is a power function, I told you, look, this it should have a shape like this. Because of that, and on the other hand, at 0 it is 1. It's like a power function. So I'll replace it by e to the power x. E is a constant between 2 and 3. So we need the factorial function as well as this. Now I'll give you the value of phi. There's another explanation to this using economics, but this should be good enough for us. When x is 1, this is e. This 1 plus 1 plus 1 over factorial 2, which is 1 over 2. This 1 over 6. This 1 over 24. If you just add these 5 terms, you get is 2.5. Okay, you get something like this. However, if you get the entire infinite terms, it should be 2.718281828. It's funny though, even though you have a pattern like this, you lose the pattern after that. Then you get something like 459. There's no pattern. And E is probably the fifth most important constant in mathematics. 0 is the most important constant because it's additive identity. You can add 0 to any number, it doesn't change the value. 1 is the next important constant because if you can multiply a number by 1 without changing its value, that's called the multiplicative identity. Third is pi, you know what it is. Fourth is I. I is the square root of -1. Oh, you can say that I squared is equal to -1, something like that. Fifth one is this, E. You can model, the existing phenomena in nature by E, right? In particular, in the university, you might get a lot of applications of E, like how to charge a when a capacity is charged, it is charged according to E. But you have still not you haven't encountered capacitor set in physics. Therefore, it's kind of beyond our scope at this point. But this is very useful in the university. I would say like that. When you do engineering, you always need E, and at the same time, you better have a good hang of that. Now, even though I went through this for your knowledge, I mean, you need better to have a little hang of that like this. You don't have to memorize this at this level. E is something like that. That's all what you need to know. And The most important thing is these two. I mean, there are two important things. The most important thing is this. You know, f dash x is fx, right? If fx is e to the power x, that's how you proved it, right? For this one, f dash x is equal to fx. F dash x is the derivative of the function. So you can write it like this. Now I replace it by ex. In fact, this is the easiest function to be differentiated because you get the same. Yes, since it's a power function, we use it. We uh, use some constant e without actually knowing what e is. In fact, e turns out to be something like this: the graph of e to the power x. It is, as I early indicated, it should be like this. It is always positive because it's a power function. At this point, it is 1. This e to the power x. If it is 2 to the power x, if it is 3 to the power x, this is, so it lies between 2 to the power x and 3 to the power x because e is something like 2.71828, right? And in fact, the graph of this e to the power minus 6, it is like this. Okay, take x is equal to 1. When x is equal to 1, it is equal to e to the power minus 1. Means when x is equal to 1, the value you get for this function is exactly equal to the value of this graph when x is minus 1. When x is 1, you get the value of uh, this function at minus 1. Therefore, it is like a mirror image of that. You know, when x increases, it is in fact 1 over x, right? E to the power x means 1 over x, 1 over e to the power x, because this is a negative power. If I have to make it a positive power, it goes like this. So 1 over e to the power x is like this, because when x increases, it decreases because of this, because e to the power x increases when x increases. However, it is 1 over e to the power x. Therefore, its value goes down. This is again 1. Like, for example, if you plug in minus 4 for x, it is e to the power 4. So it is equal to, I mean, it's greater than 1, you know. It's like that. Basically, if x is replaced by minus 6, you can simply take the mirror image of the original graph about y-axis. So basically, that's what you have. So you need these two. You need this for integration, and you need this uh, for the problem 7 or 6. Problem 6 in PO paper. Right. Now we'll do some examples. This is where we have stopped, I guess, last time. Right. Okay. If you take the first example, you have to use the function of a function, the concept of the differentiation of function of a function. Now, you know from this, when you differentiate the exponential function, you get the same. So you assume that what is sitting inside is just a single variable. That's how you differentiate a function of a function. So when you differentiate this, you get e to the power 2x. However, here here what is sitting inside is 2x. So its derivative is 2. So you have to multiply this by 2. I'll do it in the front. Hmm. Now e to the power x, it is simply, oh, sorry, dy by dx is e to the power x. You take one at a time. Now this is e to the power minus 6. Again, this case is the same. When you differentiate the exponential function, you get the same. However, you instead of x, you have minus 6. So the derivative of minus x is minus 1. So this is, e to the power x minus e to the power minus 6. The third. It's a product. So you uh, differentiate it like a product. E to the power x times, I'll do it like this, times the derivative of cos 6. In fact, you don't have to do it like that. For the sake of clarity, I'll do it like this. Now, next time you keep cos 6 as it is, differentiate e to the power x. Now, this is, when you differentiate cos 6, you get minus sin x. I write the minus sign in front. When you differentiate e to the power x, you get the same. And that's it. Now, when you differentiate this, you get the same. However, we considered x squared as a single entity. So in differentiation, when you do that as a function of a function, you differentiate x squared and you get 2x. Okay, next one. When you differentiate e to the power sine x, in fact, when you differentiate it, you get the same because exponential function spits out the same derivative. However, what is sitting inside is not x, it is sine x. So multiplied by the derivative of sine x, which is cos x. Finally, now here you have this entity, however, it is the exponential function. So you get the same thing. Afterwards, you have to multiply it by the derivative of what is sitting in the exponent here. When you differentiate cos 2x, you get minus sine 2x. However, now 2x is not x, it is something else. So you have to multiply it by the derivative of 2x, which is 2. When you differentiate this, you get cos 2x. You get cos 2x. And the derivative of 2x is 2. So this is simply the derivative of what is sitting up there. So that's how you differentiate functions involved in, functions, I would say it like this, the exponential function or various forms of exponential function, right? Now we'll go for natural logarithmic function because we need them right? We need them for, before that, okay, no, we first go through this, then we'll go for successive differentiation, and then we can start kind of integration. Okay. Okay, natural logarithmic function. Now we have to, okay, consider what logarithm is first, because it's totally new. Okay, we'll try something like this. Rather than using, okay, I first tried the exponential form, then I convert it into logarithmic form. Hmm. This side logarithmic form, not log form, it should be logarithmic form. I'll write something pertaining to base 10, right? Say, it's 10 to the power 3, or say something like this, 5 is 10 to the power, it should be in fact 90. If you go for 4 decimals, it should be 90. If you take, for example, 70, okay, then we'll go for this 10 to the power minus 2. So if you write these things in logarithmic form, right, the base is always 10, right? Therefore, it should be log 10. I later replace it by G, log LG, log 10. And always the logarithmic function spits out the power. Power is 3. So that number 1000 should come here, should fall into that trap. Now, next one. Now, if you have this, again, the logarithmic function spits out this value. That's what you get from the log table. The value is 5. Now here, the logarithmic function always spits out the power. Here the power is, or the exponent is 1.8451, and this is 70. Finally, because people don't like logarithm very much. That's why you want to come up with, start from the scratch. Here again, the base is 10. Because it is like 10 to the power something, right? So this something, or the power, or the exponent is what this logarithm function gives us. So here it is 1 over 100. I would say 0.01. That would be better, right? Otherwise, it's a little confusing here. It's simply 1 over 100. Now, LOG, logarithm, base 10 is something special. Therefore, we have a kind of an abbreviation. This equivalent to LG 1000 is 3. Only basically in Sri Lanka, we have this notation. In other places, they usually write this. This LG of 70 is 1.8451. Now we'll go for the exponential function, natural exponential function. Right. Again, the exponential form. We do it like this. You can write 10 is equal to e to the power 2.302. Or you can write 7.389 approximately is equal to the power 2. Right? Or you can write 20.08 is equal to e to the power 3. Now, these are the exponential forms. If you write, I write y is e to the power x, and I do it in the other way around. X is e to the power y. Now, in this case, if you write it in terms of e as the base, e is the base now. E is the base. So it is log e, like this. And this always spits out the logarithm function always spits out the power. It is 2.302, the exponent. Here the value is 10. Now, in the second case, here again the base is e, right? The exponent is 2. Now go for this. Here the exponent is 3. base is E. So the exponent is, hold on. Here I have made a mistake, right? Here I have made a mistake. The logarithm function always spits out the power or the exponent. It is 2. This value is 7.389. Here again, the case is the same. The logarithm function always spits out the exponent. Finally, there are two more. Okay. Here, look what happens. Now, in this case, E is the base, log E, right? Logarithm function always spits out the exponent, so it is X. So Y comes here, right? On the other hand, the last thing, look what happens here. Now, E is the base still, but the exponent is Y, so it will give you Y, and the other value is X. You know, logarithm is in fact the inverse of the exponential function. Here, look, when X is given, you can find Y. Here, when Y is given, you can find X. Here, when Y is given, you can find X in the exponential function. Here, X is given, then you can find Y. So it is exactly the inverse. Here, Y is the independent variable. You can write X in terms of Y. Here, you can write Y in terms of X. Now, again, this is a special case. Universally, we have a different notation for this. This probably, LG is not used everywhere, but in Sri Lanka we use. But here, this is used everywhere, universally. Log E. Now, this is the natural exponent. But why do you say that? How do you say that it is natural exponent? Okay, I'll give you the reason. Hmm? It is totally beyond our scope, but I'll show you why. I mean, why this turns out to be the natural exponent. Anyway, for the time being, you have to believe me. Okay, this is the natural exponent. Soon after this, I'll explain. I mean, after explaining this, I'll explain you why E turns out to be the natural exponent. 10 is not the natural exponent. We use that. We use 10 as the natural exponent because we have 10 fingers, 5 here and 5 there, altogether 10. So for counting, we use 10 as the base. However, when it comes to logarithms, 10 doesn't work nicely. I'll show you how. Hmm. Right. Now, since it is a natural logarithm, like you replace this by LG, natural logarithm. Natural means it starts with, not means, it starts with N. So natural logarithm, they write N, Ln, not NL, Ln. 10 is 2.302. Because I can just give you the formula and do the problems, but it doesn't make any sense. When you go to the university, you might run into various difficulties if you do that, right? Mostly in the universities, we have produced most of the best tops. Hmm. For example, like these days in Perera, there are 6 batches, right? So like 20, 21, 22, 23, 24. Apart from 22 batch, all the batch tops in Peradini are from our class. Like 20, um, there's a computer engineer student. He is a batch top currently. 21, there's an electronic engineering student from high school. She's a batch top. 22, we don't have anybody. Like all top 3 are from Colombo. In 23 batch, top 3 are all from first, second, and the third. There are 3 students who got perfect GPA. All are from our class, and 24, they haven't taken any exam yet, but the best student from A-level results is from our class. So it's like that. So even in Jaipur, there are two currently. Even in science faculty, some of them are best ups. So therefore, I mean, if you want to perform in the university as a top-notch student, you need to understand the subject like this. Later we can forget it, right? But you need to see it like this, right? Uh, Otherwise, I could have straight away tell you, okay, this just the inverse of this is a natural logarithm, which is denoted by ln, and this is how you differentiate. Differentiation is so easy, but you need to know what's going on here. Otherwise, you cannot connect this knowledge with what you are going to learn in the university, right? Okay. Now, again, if you replace it by ln, it will appear like this, right? It is 2. This is 20.08 is 3. Now, here it is L in Y is X. So if you have something like that, you can write it like this using the exponential function. Here X is the subject, here Y is the subject. So they are, inverse functions. Again, the last, right? This is, L in X, natural logarithm of X is equal to Y. Here we have made Y the subject. Here we have made X the subject. Same thing, but the appearance is different. So the inverse of this is that. Now I'll show you why E turns out to be the natural exponent. Hmm? The reason is this. I'll just show you some numerical example. Okay, I should be able to figure out this, right? Now there's a pair of numbers. I'll write smaller number raised to the larger power, larger number raised to its smaller power. I'll write it here. No, 5 to the power 6. Okay, 6 to the power 5. Now we'll compare those. Now look, all these numbers are greater than E. Now if I take two numbers which are less than E, 1 to the power 2, 2 to the power 1, 1 to the power 1.5, 1.5 to the power 1, 1.5 to the power 2, and 2 to the power 1.5. Or both are less than, both numbers 1 and 2, 1 and 1.5, 1.5 and 2, both all that pair is less than E. Let's see how that is behaved. Now, what is the value of this? 7 to the power 8, 8 to the power 7. 8 to the power 7 is a huge number, we'll see. We'll write those numbers and see how they behave. Here, I think I need some digits here. I'll write 10 to the power 6 somewhere here. This is 5 to the power 6, 6 to the power 5. I'm going to compare these. Right? We have a pair. Smaller number raised to the larger power, and I have solved those places. 6 to the power 10, 10 to the power 6. Now, if you just find the values of these, we'll see what the values of these are. It is a little hard to compute, though. 8 to the power 7 maybe, we'll see what it is. 8 to the power 7. 8 to the power 3 is 4096. So 8 to the power 6 has so many digits. 16777,216. So if you multiply it by 8, I'm in little trouble here, but I'll try to figure that out. I need more space here. Anyway, I'll write it in small letters. 777216. Okay. So you get 4. Kind of a little unfamiliar number to me. I think that is kind of wrong, right? 16777,216. Yes. Something like that. 7 to the power 8 is this. It is here you have 1, 2, 3, like 6, 7 digits. I think here this may be wrong. I'll just calculate this again. Yeah, I made a mistake there. Because 8 to the power 3 is not that. 8 to the power 3 is 512. So it's guys that okay. It is this. Now look, we have 7 digits. We have 7 digits, but this is larger. Because this starts with 5, this starts with 2. 6 to the power 10 is something like this. 10 to the power 6 is something like this. So here you have 7 digits. Here you have 8 digits. Clearly this is greater than 10 to the power 6. 5 to the power 6. Here I made a mistake. In fact, I have computed 8 to the power 9 or something like that. Yeah, earlier. It's wrong. Huh? 8 to the power 9, yes. Now here, this is, 5 to the power 6. 5 cube is 125. Therefore, 5 to the power 6 is this. 6 to the power 5 is this. So it has more digits. So clearly this is greater. So when the numbers are greater than E, this number is the smaller number raised to the larger power is always greater. 10 has nothing to do with this, right? And on the other hand, if you take this, this is 1, this is 2, this is greater. So here the larger number raised to the smaller, raised to its the smaller power is greater. This is just 1, this is 1.5, so it's greater. Then the inequality is in the other way around now. This is 2.25, this is 2.828, like 2 to the power square root, 2 to the power 1.5 means 2 times square root 2. It is this. So it's greater. Now, what happens if the numbers are like this? 1 is when both are greater than E. Is when both are greater than E. E means 2.7. When both are less than E. You don't have to memorize these values, so memorize this concept, but I'm just trying to convince you when both are less. Sorry. Now, what happens when one is less and one is greater? Here, it demonstrates some weird way. Like, take this, for example, 2 to the power 3 and 3 to the power 2. Here, numbers are small, so we'll do it like this. 2 to the power 4 and 4 to the power 2. 2 to the power 5 and 5 to the power 2. Always what is sitting in front is smaller power raised to the larger power. This is 8, this is 9. This side is greater. This is 16, this is also 16, equal. This is, 32, this is 25. So you cannot say when one is greater than E and the other is less than E. You don't need this for differentiation, but this is what E turns out, this Y, E turns out to be the natural exponent. And using graphs also I can explain it, but that's a little too much for you. You don't memorize this, huh? I mean, that's the reason for that. Now, we'll see how we find the different derivative of log x, right? So this is a basic idea. Right. So we'll try to find the derivative of logarithm. However, before that, we need to go through the graph of the logarithm function. Now, look, again, we'll go there and see what it is. Y is equal to log x. This. It is, okay, it is exactly the same, but here y is the subject, here x is the subject. Therefore, they are, inverse functions. So if one is the inverse of the other, you have this shape. Exponential function goes like this. Now this is y is equal to x. Gradient is 1 and it goes through the origin. So the inverse function, the graph of the inverse function is exactly the mirror image of this. Mirror, because when you take the inverse function, you have to interchange x and y. Because of that mirror image like this. This map to this. This is 1. So this is y is equal to natural logarithm x. There's a graph of that. Now we'll try to go through the derivative of log x. It's something that I need to write here, but not now. I'll do it later. Okay. So we'll start with y is equal to log x. We don't know how to differentiate this. Therefore, we take the inverse function. Now we make x the subject, x is c to the power y. Because if you have this, you can write it in logarithmic form. How do you write that? If you have it, you can write it like ln or log e. Now, always the logarithm function gives you the exponent. So it is y, this value is x. So you can write ln x is equal to y. It is exactly this. So if you have it like that, you can write it like this and then this. So all are the same. Both are the same. Now, you differentiate now. X is the subject. X is expressed in terms of y. Therefore, by differentiating with respect to y, you get, when you differentiate this, you get the same. Here you get dx over dy. But what you need is dy by dx. If you take dy by dx from dx by dy, you have to get the reciprocal. Now, in fact, e to the power y is x. So dy by dx is 1 over x. So it's easy. Y is log x. However, it's not complete because sometimes, you have mod x there. Now, I'll sketch the graph of that. I'll sketch the graph. Uh, if you have mod x, now look what happens. Say, okay, log x. When x is, okay, if you want to graph it like this, it should be in this way. Log mod x. I hope I can do it here. When x is greater than or equal to 0, because when you have mod function, you can break this into two pieces. Right? When it is greater than 0, you just get log x. Right? Because when x is greater than 0, you can replace this by x. When it is less than 0, you can write it as log of minus x. That's how the modulus function behaves. Now look, if you take when x is greater than or equal to 0, here equal to when x is 0, log 0 is not defined. So I'll write it like this. When x is greater than 0, it is like this. When x is less than 0, it should be log of minus x. Now, at least when x is greater than 0, it should be like this. Like this. This one. So that part is correct. When x is greater than 0, it is exactly like this. Okay, when x is less than 0, how do you sketch it? When x is less than 0, say, okay, take some value. Okay, when x is 2, it is log 2. When x is 2, it is log 2, right? When x is minus 2, what do you get? Okay, when x is 2, remember, it is log 2. Right? When x is 2, it is log. I'll take some value. When it is 2, this height is log 2. Just an example. Or I can take any a. At a, it is log a. What about at minus a? When it is minus a, exactly here. When you plug in minus a, log of minus a means log a. Again, it is log A. So you get the same value. Likewise, when you take any other value, you get the same value. So you get a mirror image of this -1. You get exactly the mirror image of that. Now look, now the gradient is, here the gradient is this. We know that the gradient is 1 over x. So here the slope is, I'll write m, is 1 over a. Now at this point, slope is like this. By symmetry, they are in magnitude, they have the same slope. They are symmetric. Therefore, the magnitude of the slope is the same value. However, this is positive, this is negative. So it is negative of 1 over a minus 1 over a. This, if it is 1 over a, same magnitude, however, it is going down. The slope is, it is a downward slope, it's upward slope. Therefore, m is minus 1 over a, means I can write it like this. Same thing, 1 over minus a. Now look, when at a it is 1 over a, at minus a the gradient is 1 over minus a, right? What does that mean? No matter what the value is, you can find the gradient by taking the reciprocal of that. The method positive value a, so it 1 over a. Now if you have minus a, it's only 1 over minus a. Whatever it is, no matter what the value is, you just get the reciprocal. The reciprocal will give you m. M is the gradient. Gradient is the rate of change. So the rate of change is simply the reciprocal. Now this is, I told you, this incomplete. Now this is what we need. Now using this graph, I am writing this. Logarithm of mod x. Logarithm of mod x is simply, if you take this, if you take this graph, you can see that here the gradient is 1 over a, right? From this, I got it from this, because it is log x, its derivative is 1 over x. So at a, it is 1 over a, because this is exactly log x. However, when you take log of mod x, you get another part like this. It is because of this. When x is negative, it should be log of minus x. For the minus 0 log mod function, when x is greater than 0, it is x. When x is less than 0, it is minus x. So that's how mod x is defined. Now, if you take a value like this at minus a, because of the shape of the graph, same value, because it is symmetric about the y-axis. Same value for the gradient, but this is a positive gradient. This is increasing, this is decreasing. Therefore, from the graph, you can say if it is 1 over a, this should be minus 1 over a. Now, you can incorporate this minus sign here. What does that mean? When the value we can reciprocal gradient again. So where it is, no matter what the value of a is, you can always, okay, if you have this, it is just 1 over x. This is what we need, in fact. We don't need the rest. Rest is there just to explain what it is, right? But you don't have to, you can take that down. But for A-level differential calculus, you don't need this. But you better have a little neck on this, little hang of that. If you have that, you can do better when you're in the university in future, right? So that's why, that's a notation. This is the reason for E to be the natural exponent. That make the decom e to value have smaller value raised to the larger power is greater. Make it decom less than larger power raised to the smaller power is greater. Make it අපිට කියන්න බෑ. 10 වලට එහෙම සීන් එකක් නැහැ. 10 වලට කොහොම ගත්තත් මේක එක එක අතර තියෙන්න පුළුවන්. Now, around numbers, the powers behave in a different way. ඒක තමයි අපි මේක ගන්න natural exponent එකට. And in differentiation and everywhere in calculus, you get uh, ln rather than lg. Now, we'll differentiate. In fact, this is what we need for calculus. But if I just teach you, okay, this is how it is differentiated, it doesn't make any sense, right? I mean, you can get the answers, you can differentiate it, but uh, you lose a lot of background material there. Hmm. So you will run into problems later. But when it in the context of the exam, if you consider the context of the exam, or if you look into this from the examination point of view, you don't need this. You need only this. If y is this, dy by dx is simply 1 over x. 1 over what you have there. 1 over what you have there. But however, there's something. This is not x. Instead of x, you have, right, compared with this, you have x squared plus 4. So use the concept of the differentiation of function of a function. That make a different derivative of 2x. You have to multiply it by 2x. So it is like this. 2x over x squared plus 4. I'll do another. Here, dy by dx is simply 1 over x, 1 over what you have there. Like this. However, the function sitting inside is not x, it is x minus 3. So you have to multiply it by its derivative. However, its derivative is 1. When you multiply something by 1, it doesn't make any difference, so you can leave it like that. We take something like this. Sorry, it's y, it should be y. So by differentiating this with respect to x, logarithm of this, no matter what you have there, you take the reciprocal. Because it is 1 over x. After that, you consider this as a single entity. So you multiply this by its derivative. Derivative is 2x plus 1. Now, say you have log x to the power 17. Now, don't worry too much about this. Using the properties of, before differentiating, using the properties of logarithms, you can write it like this. You can pull out this 17 in front. Now differentiate. If you have a constant in front, when it's a, when the function is multiplied by a constant, you leave it like that. Now the derivative of log x is 1 over x. That's it. I'll do one more here. Something similar to that. First, pull out 4. I'll do it like this. Something more complicated. Again, using the properties of logarithms, you pull out 4. Yeah. So it is simply, I better put modulus. Here, modulus is not needed since it's a fourth power. Fourth power is always positive. Now, 4 Now, what you have here is x plus 2, take the reciprocal. The derivative of this is 1, so you have to multiply it by 1, but no point of doing that because it doesn't make any difference. This is in fact 17 over x. Right. Okay. Now we went through that as well. Hmm. Now, I just give you some time just to take that down. Then we'll start integration. We use these concepts in integration a lot. Hmm. Just take a short, like 2 minutes to take that down. Right. Right. Uh, I didn't go through, like, after finishing differentiation, I went through applications of different derivatives and graphs. But I deliberately postponed covering the other parts, like inverse trig functions, logarithms, and exponential function. There's a reason for that, because they are there for integration. Hmm. I just start the basics of integral calculus. Uh, Even though I started today, I'll do them. Do this. I'll go through the same thing next week when you physically meet you guys. When I physically meet you guys in the class. Okay, integral calculus introduction. Integral calculus can be reckoned in two different ways. One is antiderivatives, the opposite of the differentiation, or summation. Summation of small parts, like uh, in ICs, in integrated circuits, you have small parts, and it's a integration of all those small parts. ඒ කියන්නේ පොඩි පොඩි කොටස් එකතු වෙලා හැදිච්ච ලොකු එකක්. Integrated circuit කියලා කියන්නේ IC කියන්නේ. The integral calculus has the same meaning. ඒක අපි I mean we sum up small parts to get the complete value or the full value or full complete area, complete mass, whatever. Okay. Now first I'll go through the basic stuff. Hold on. I first show you this. Say, for example, this antiderivative business. Say this is gx. say the derivative of this is gx. In fact, it is f dash x. I just take it as gx. Now, you multiply, cross multiply this. Now, to get rid of d, you do this. This is the integral. This is the antiderivative. We denote it like this, and this goes away with this d. Don't do it like this, huh? I'm just indicating what happens here. This d, this like d inverse kind of thing. Integral, antiderivative. So these two will go away. Derivative operator will go away with this. It's kind of inverse derivative operator. Now look at this. When fx is inserted into this operator, you get gx. Here gx is inserted into this operator, you get fx. This is in fact the antiderivative, or the reciprocal of, not reciprocal, inverse of the differentiation. We call it as antiderivative. This derivative of this is gx. The antiderivative of gx is fx. Right. Now when you have this, you can straight away write it like this. It's okay. You don't have to go through this process. Now, now this is how it works. Now, as I told you, I deliberately postpone those things. I first take this, for example, the derivative of x to the power n plus 1 over n plus 1. I add another constant. C is a constant. Here n is not equal to minus 1. If n is minus 1, this will blow up. What is this? If you differentiate, you get 1 over n plus 1. It's a constant. When you differentiate this, you get, okay, bring n plus 1 to the front, subtract the power of x. So it is x to the power n. Anyway, the derivative of c is 0. Now the derivative of this is x to the power n, right? Like this. Now, if you put that x to the power n inside the integral, right? I don't have to go through this process all the way, every time. If you want, I'll just do it for this particular problem. This x to the power n. Now I cross multiply. But next time I wouldn't do it like this. Now use this. Now these two will go away. C can be any constant, and here I forgot to write this. N is not equal to minus 1. Now with this, now I'll write this in front. I mean in the left-hand side, not in front, in the left-hand side. So this is in fact our first formula. Right, when you differentiate this, you get this. When you integrate this, you get that. Next time I wouldn't go through like this. Now, this A. I should have, written this. Now the integral of, we'll say 1 over x. We'll try to find that. 1 over x. When you differentiate logarithm, you get 1 over x right there. I mean, you need this not for derivatives, but for integrals. Okay. The derivative of this is 1 over x. Now you can write it as an integral. So when you put this in the integral, you get that back. But I'll do some little change. Yeah? I add a constant. Even though I have a constant there, still it is 1 over x. Because the derivative of this is 1 over x, this is 1 over x plus c. It is again 1 over x. So when you have 1 over x there, you may get something like this. C can be any constant. If you put 0 there, still you get it is correct. If you put 1, it's correct. Now, that's our second formula. This is exactly the reverse thing. When you differentiate this, you get 1 over x. When you integrate it, you get this back. The third one. Then we'll do some examples. Huh? The third is this. When you have some function here, and you exactly have its derivative up there, right? When you differentiate this, look what happens. If you differentiate, logarithm of fx, when you differentiate something like this, like this, for example, you take look at here, you take the reciprocal, right? Then you multiply it by its derivative. Now, we do the same thing here. You take 1 over x, 1 over fx, then the derivative of what you have there is f dash x. The derivative of c is 0. So this is simply f dash x over fx. So when you differentiate this, you get that. So when you integrate it, you should get this back. That's our third formula. Even we can do some problems from these. But yeah, we can do some problems. D. We have in fact two more formulas, I guess, right? C. Linearity means this. The very basic mathematical operations we learned at school, like when we were in our grade 1, grade 2, multiplication and addition. So if you have something like this, say A is a constant, A times fx plus B times gx, like in the derivative, differentiation, like in sigma sign. When you have two of them, you can take one at a time. And at the same time, when you have constant in front, you can pull that out. So a times the integral of fx plus b times the integral of this. Like in the sigma notation, like in derivatives, you can do it like this, one at a time. But if you have a constant in front, you can pull it out. Hmm. There are in fact three more formulas, but first we'll do problems from these four. Hmm? Okay. Otherwise, it will be too much. If I list all of them, it will be little overwhelming. We'll do some examples from this. We'll later take care of the other three. Right. Just take that down. Then we'll do some examples. In fact, this idea is also not very frequently used at this level, but this is how you do it. Huh? You first cross multiply this and introduce this sign to both sides. This, in fact, the inverse of D. But we don't write D inverse. Huh? We write this notation. So this will go away. It leaves you with fx. Here you have gx. Here this is the, okay, you can call it as gx is the derivative of fx. Fx is the antiderivative of gx. So we did exactly the same here. But after that, once you have it, have something like that at your disposal, you can straight away write it like this. Similarly, if you have this, you can write it like this. Integral of this is equal to that. So you take that down. Then we'll do some examples. And with those set of examples, we can wind up. That's good enough for today. Right. So I'll put down the summary again, and we'll do some examples using them. Now, first I'll write this, but there are 3 more formulas to come. So this is first. So this is the whole idea of this. When you have some power, n plus 1 means power is increased by 1. When you have x to the power 6, now problems will be extremely easy, right? When you have x to the power 6, this should be x to the power 7 over 7. That's all what you need to do. Now the second, when you have 1 over x, when you differentiate this, you get 1 over x. When you integrate, you get that back. So 1 over x dx. Now c can be any constant. Third, f dash x over fx. It turns out to be log of fx. Because when you differentiate this, you get that. Now, if you have something like this, any function in the denominator, and if you have its derivative at the top, you can write it like this. And finally, one at a time thing. Multiplication and addition doesn't harm the final result. I mean, you can take one at a time while pulling out the constant in front and integrate, or you can simply integrate this at once. Both are the same. So the integration preserves under addition and multiplication. Right. I'll list that as well. I write it like this. A times the derivative of, integral of fx plus b times in all these cases, c is called an arbitrary constant. It can be any constant. We don't know what the value of that is. Arbitrary constant. That constant can be anything. You need some condition. If you want to precisely find C, you need some condition. So that's beyond our scope at this level. Now we'll do some examples. Now the problem was simple, right? Okay. I'll add one thing. When you differentiate kx, right? When you differentiate kx, what do you get? Mx plus c kind of thing. You get k. The derivative is like if you have mx plus, I'll write mx plus c. You get m. Why? if y is mx plus c, it's a straight line, its gradient is same. On the other hand, if you differentiate this, you get what? M times 1 plus 0, m. So with that setup, if you integrate this, you get mx plus c. You get this back. Right? Okay. Right. We'll do these six first. Now, you know, this is one at a time thing. So when you have x cube, this is how you have to do it. You increase its power by 1 divided by the same number. So this x to the power 4 divided by 4. Hmm. Now you have 4 you have 4 there like this. When you have 4, it should be like 4x plus c. If you have 4, it should be 4x because when you differentiate 4x, you get 4. So when you integrate 4, if you take the entire derivative of 4, it should be 4x. You have to put c at the end. C is an arbitrary constant. This one. Now you have sum of two functions. So here 2 times the integral of x, right? 2 times this. You get, when you have like two functions, you take one at a time. When you have a constant, you can pull it out. So you have x. How do you integrate x? X to the power 1. So do it like this. Increase the power by 1 divided by the same. Now this 5, it turns out to be 5x plus c. Now you can simplify this a little bit. X squared plus 5x plus c. Now if you differentiate this, you should get this back. Let's differentiate. When you differentiate, you get 2x plus 5. Exactly this. Here. One at a time. You take this first. Pull out 4. Integrate this. X to the power 3. You increase its power by 1 divided by the same. When you have x to the power 1, increase the power by 1 divided by the same. It's wrong. This is wrong. Here we have to increase the power by 1. It should be 4 divided by 4. Minus, when you have 3, it is minus 3x. Because when you differentiate this, you get 3. Finally, you add a constant c. You can simplify this a little bit. C is an arbitrary constant. Right. Now take this. Now it turns out to be little, it takes a new turn now. When you divide it by x, you get 1 over x. When you divide this by x, you get 1. Oh, wrong. Sorry. X squared divided by x is x. Now this is 1 over x. Now ready to differentiate. Now, ready to be differentiated. Now, what is this? When you integrate this, not differentiate, we take the antiderivative. Sorry. So you increase the power by 1 divided by the same. When you have 1, it should be x. Because if you have m, it should be mx, like that. Now, new thing, 1 over x. When you have 1 over x, it's log x. All these will give you a constant. You sum them up and write it as c. Don't write like this plus c1, this plus c2, this plus c3. Just add all of them together and write it here. Here. With this setup, you don't know what to do. We'll simplify this. Now integrate. This is x. If you have m, mx, like that. And now this is, one at a time. You take one at a time. Here you can write it as 3 times 1 over x. Right? So write 3 in front. 1 over x, the integral of 1 over x is log x. Now write the arbitrary constant at the end. Because when you differentiate that, c will go away. This one. 1 over x minus 4. You can do it like this. The derivative of x minus 4 is 1. Like this. Or you can even use that. In the place of x, you have x minus 4. But I think I'll be able to use this for the time being. Because there's one thing I have to tell you. So it is simply log x minus 4 because, look, if you have a ratio like this, when you have any function at the bottom, and if you have the derivative at the top, it is simply log of the denominator, log of the bottom. So log of this plus c. Right. You take that note and I'll do some more examples. We'll go through another set. First, go through this. We will do some more problems. Right. We'll take this set. Now the first is quite straightforward. You take one at a time, and if you have x to the power n, you have to increase the power of x by 1. That's why you have n plus 1 there. So this is x to the power 5 over 5. This is x to the power 4 over 4. This is x to the power 3 over 3. It is x to the power 1, so it will be x to the power 2 over 2. 1. 1 is just x, like k is kx, like that. So you have, you get few arbitrary constants, you sum them up. Where c is an arbitrary constant. Right, write it there. Now here, you cannot do anything with this. You multiply. You get x to the power 10 plus x to the power 5. Now you can do it. Take one at a time. This x to the power 11. Increase the power by 1 divided by 11. Increase the power by 1 divided by 6 plus c. At the end, you have to introduce a c. Now, if you have of any function and its any function and at the bottom and its derivative at the top, like this, look. When you differentiate, you get 2x plus 1. You can straight away write it as log x squared plus x plus 1, then plus c. Here, this is x cubed plus 1. When you differentiate, you get 3x squared plus 0. Basically, 3x squared. Now, with this setup, you have the function and its derivative at the top. You can simply write it as log denominator, log of the denominator. Then you write c. Because when you integrate, when you differentiate it, this will be 0. Its effect will be 0. So to be more general, you introduce a constant there. Now here, take one at a time. This is 1 over x. You know, it is log x. This is x cube, you know, x to the power n, x cube over 3. Then you get two arbitrary constants, you sum them up and write it as c. Here, take one at a time, but if you have a constant in front, you leave it like that. And it is, you know, x to the power 8 over 8. This is 5 times x to the power 10 over 10. When you integrate 7, you get 7x. Now, all these arbitrary constants can be summed up to c. Now, you can simplify this. This is x to the power 10 over 2 plus 7x plus c, where c is an arbitrary constant. I just want you to, you know, be familiar with these things. And next time we'll do some more examples. And there are 3 more formulas to come using inverse trigonometric inverse functions and the exponential function. So we get 3 more. Then we can, with those, we can even go through partial fractions next time. How to integrate expressions, I mean functions using partial fractions. Okay. So you take this down. Problems are easier, but you know, we need to understand what natural logarithm is, what exponential function is. Even without any idea, you can do these problems by heart, but that's not the way to learn it. You can probably get through A levels easily, but after that, you will run into all sort of problems when you're in the university. So you better have a little hang of that. Hmm? Right. Right. So that's it for today. But next time when I start the class, I just breeze through the integration part and we'll do some examples. And there are 3 more formulas to come. Once we have everything at our disposal, we can easily do the rest. Hmm? Right. We'll start papers next week. Right. Okay. So I'll See you next Wednesday. Hmm? Since schools will start next week, I guess. Therefore, we have to, I don't know what happens in Candy. For the time being, assuming anyway, we cannot have an extra class next time. So we'll meet as usual by 3:30. So it will be from 3:30 to 6:30 next week. Hmm? Okay. So I'll see you next Wednesday.